Thank you for the introduction. So then let's jump straight away to the next slide. So let me start with the description of the problem domain we want to tackle in this work. So basically, we want to come up with a methodology to develop turn-based games, for example, chess or Go, or also card games. And on the other hand, the methodology should also provide AI players for the games so that we can play these games out of the box. And on the other hand, or first of all, these AI players should also maybe come in different variants. So for example, to provide different difficulty levels, or to provide players with different traits maybe. And furthermore, of course, the developed game should also include the human player so that we are able to basically provide some user interfaces and some means for the user to play the game. So let's jump to the solution domain. How do we want to tackle this? So there are two main components I'll be talking about. The first one on the right-hand side is a game description model, a game description language basically, which we are going to use in order to model the game, the players, the rules of the game, the states, and so on. And on the other hand, to develop the players of the game, we want to use AI techniques, so basically neural networks, which then basically will respond to the players' inputs and create turns of themselves. And these two models we then want to input into a holistic toolchain, which will then generate code to execute the game, to train a neural network player, to provide maybe several neural network players to execute the code, and will provide also user interfaces, APIs, and also hook points to maybe extend the game with custom interfaces and so on. So let's first have a look at our game description language. So game description languages are logics-based languages similar to Prolog. In particular, our GDL is based on the Stanford GDL, which has been developed some years ago for the domain of general game playing. So we basically use a very similar syntax, but extend the GDL by several advanced concepts. So as I said, it looks pretty much like Prolog. It has a prefix notation, but the game is much more domain-specific, of course. So we have four main concepts here, which we are able to model using GDLs. So the first one is, of course, the players themselves. So we want to basically say which players we support in our game. For example, in chess we have the role of black and the role of white. So it's two players which can play the game. Then we have to define the rules, what is allowed, what is not allowed in our game. This is seen on the right-hand side. Then we want to define the mutations. So how can we alter the state? If we come from one state, the player chooses to perform an action, and how will the state in the next turn look like? And the last concept we have here is the state definition. So first of all, we need to define how the state will look like at the beginning of the game, and of course we'll be able to alter the state while the game continues. There are some advanced concepts which we introduced, which are important, for example, for card games, such as random events. So sometimes we want to draw cards, for example, or we want to roll dice. So we want to introduce some specific notation which allows us to do this. There are concepts like hidden information. For example, if I don't know which kinds of cards my opponent has on his or her hand, and we have this simultaneous decision making. So these things we have also incorporated in our language. So maybe let's have a look at how random events are implemented. So basically for this, we introduced a specific player, which we call random. And this player has its turn whenever some random events need to happen. And then we define, okay, a legal action, for example, throw dice, and say, okay, in this event, the die should be, a value for a die should be chosen. And then we know, okay, dice have values from 1 to 6. So this will be the value will be chosen at random at runtime then. Also, in games, we often have to perform some kinds of computations, which are usually difficult to perform in logic-based languages. So we introduced some basic arithmetic operations and comparison operations, which are important, for example, if you play cards and you need to count your points and then compare the points to your opponent's points and so on. So this is helpful to do this. And also you have simultaneous decision making, which is basically implemented by introducing hidden information and then basically taking turns producing some hidden information while simultaneous decision making takes place, and then revealing the decisions of the players afterwards. So this was the first part. The second part is the neural network language, which we're using here. So basically, we use a deep learning framework, which we have been developing at our chair for several years now. It's called Montiana. Basically, from the idea, it's very similar to modern internal DSLs like Keras and PyTorch maybe. So basically, we define layers of neurons and interconnect them using this arrow syntax, which you see in the listing here in the green part of the listing. So for example, here we have a convolutional neural network, which has conv layers, which are then fully connected layers, and so on. So basically, the neural network is defined as a DAG of neural net layers from predefined layers, and then we have a code generator, which is able to produce neural network in some widely used frameworks such as MXNet or TensorFlow, and then we can train and use it. So this is basically the second model which the user needs to produce in order to create a game and a player for the game. And now, since we have incorporated all of this in one toolchain, the toolchain can infer the information on the state size and the action size, or the possible actions, from the game model, and provide us the information how the input and the output of the neural network should look like, so that we have some kind of context conditions checking that the neural network is actually consistent with the game description. So now, in the next step, we need to train the player in our game environment. So how do we do this? We use reinforcement learning, which is pretty well suited for this problem. So in reinforcement learning, we have an agent, which is basically our AI player. And this agent tries to perform some actions in the game, which means it makes some moves. And then we expect the environment to give the player some reward, and based on this reward, the agent is then trained. So this is what is depicted on the left side. And now when we move to the right side, we add the self-play component. So basically, into the environment, we introduce a copy of our trained player and let the player play against him or herself. So basically, we have a fixed copy of the player, and the trained player plays against its copy and tries to improve itself compared to the copy. And once it's improved, the copy is replaced against by the new version, and so on. So, and this way, we come up with an agent which performs better and better. So for our evaluation, we started with some very well-known games, namely tic-tac-toe, chess, and the card game Doppelkopf. Tic-tac-toe is, of course, basically the Hello World game among these games. It's very, very simple, has a very simple rule set, and should be pretty easy to learn. So here we see the learning plots for this game using different algorithms which the toolchain supports out of the box. So on the left-hand side, we see the DQN algorithm learning to play tic-tac-toe. At the first glance, it looks as if the agent would learn very well, but then if we look at the rewards on the y-axis, we realize the rewards are pretty much negative and converge to zero. which means using DQN, we only achieved that our agent was able to produce legal moves, which led the agent basically to always draw at the best. And then we also compared with different, more advanced algorithms, such as random DQN and also playing in random players, which turned out to perform much better, which is depicted on the right-hand side. So to conclude my talk, what have we achieved? So first of all, we have developed GDL with some advanced GDL concepts, enabling us to produce or to model random events, hidden information, and also simultaneous decision making, but also arithmetics for computations needed in games, and also some type system. Furthermore, the model is integrated then in this toolchain, and AI players are trained automatically so that we can come up with AI players and different variants of these AI players after training automatically. But there are also still some things to do in future research. So for example, we need to play around with different training algorithms for different games. Also, we want to enable the inclusion of heuristics to define neural network architectures automatically based on the game description, so that the game designer doesn't even have to come up with his own architectures or her own architectures on its own. Yeah, that's pretty much it, and thank you for your attention.
Thank you, Peter. Any questions?
Okay. Thank you for interesting. Just for curiosity, so for games, well, I think games are very kind of very logical thing. And I want to express many properties, invariants in the game design. So is it possible to express some kind of properties which should hold here and there, and reason about that kind of thing in your framework?
What kind of properties you have in mind?
So for example, games. So this property must be satisfied. So some if I implement chess in your framework, then there are a set of possible moves, but in Japanese chess where we cannot play. So even though this one guy should be able to move to these parts, but under the global situation, it is prohibited in some rules. Can I express that kind of constraints or properties?
Yeah. So basically, we have the legal keyword for this, which is shown here on the right-hand side. So, for example, also in standard chess, we have things which can only be done in specific situations. Like, for example, pawn movements are different in some kind of situations. So this we will do with this legal keyword. So we would define what is legal in a particular state. And
so you said that we can express this kind of local rules, but if we have a kind of global constraint or something like that, is it possible?
So you can basically do both with that. So you can at any point in time you can evaluate this. So basically you have the constraints which you can evaluate, and if the constraints are true, whether it's global or local, the move can be said to be legal or not.
I have a question. So you use a neural network to learn how to play the game. Do you have some techniques to recover what these neural networks have learned and explain it to the user of your system?
That would be very great to have something like this. We don't have this at this time, but explainability is of course a very interesting part of neural network research now. Would be future work maybe.
Do we have more questions?
I'm curious about what training the agent through self-play. Did you train just a single agent each generation, or did you train a population of agents?
So we tried different things, also populations we trained, and also in different hyperparameter settings, of course. And then we basically were stuck to the best performing algorithms.
All right, thank you.
If there are no more questions, let's thank the speaker again.